Hello and welcome back to, I think, our first topic after the progression exam. We're going to get into some integration. So in this topic, before the summer holidays, we're going to integrate quite a few of the things we learned how to differentiate back in May time. So exponentials, logarithms, sine, cosine, and other trig functions. We're not going to quite get into using trig identities, but we will be reversing the chain rule in particular. Coming to the reverse of the product rule and the quotient rule, we'll get into that later in the second year. So it's at this point I want to draw your attention to something that you've probably seen in the formula book, but probably not really paid much attention to. We looked at it a little bit in differentiation, but it really comes into its own when we start to integrate. And it's these two sections. You're given this section on the left, differentiation. You're given your first principles formula, which we're not really going to look at in this topic, but importantly, we're given this set of trig derivatives as a standard. So we know that if we differentiate tan x, we've got sec squared x. Okay, we can just use that as a standard result. We may be asked to derive it, but actually we can just look it up and use it as a standard result. Now that works in reverse. If we know we have to integrate sec x tan x, for example, we can just use this piece of information to see that it would integrate to sec x. So you can see that we're using this section in reverse. We're given f of x and f dash x. So if we need to integrate something that looks like this in the f dash x column, it integrates back to the thing in the left-hand column. So that's one of the sections we need to use. And then confusingly, thanks very much at Excel, we also have this in the formula book. Now this follows a different format. In this one, we've got f of x on the left, and then on the right, we've got what happens when we integrate f of x. Okay, so if we integrate sec squared x, we get tan x. It's exactly the same result as this first line on the left, but obviously we're going from the left column to the right column for integration, whereas in this one, we're going from the right column to the left. Now, yes, it does seem confusing, but if you understand your notation, it's not confusing. So let's look on this right-hand column again, see if there's anything else, because obviously this result here is in both sections. Here, we can see that if we integrate tan x, we get log sec x. Now, with the k's, obviously we'll get into that, but that's just reversing the chain rule. So tan x integrates to log sec x. That's not present in this first list, so this second list is useful. We can see if we integrate cot, we get 1 over log sine. If we integrate cosec, we get something that looks quite involved, minus log cosec x plus cot x, and etc., etc. This little formula at the bottom is called integration by parts. We'll come back to that in the second year, so you don't need to worry too much about it right now. So let's get into some examples of the type of function we're asking you to integrate in these 4 lessons that we've got. I'll show you how I use these standard results as we go along. So here's a first example. We're going to evaluate these integrals. Now, we know that when we integrate a function, and say for example, and this is just an example, I asked you to integrate x cubed plus 4x squared plus 3 with respect to x. You integrate each term in turn, don't you? You do x cubed, you add 1 to the power, you divide by the new power. You look at 4x squared as a separate thing, you add 1 to the power, you divide by the new power. So essentially what you're doing here is actually 3 integrations. You're integrating x cubed with respect to x, you're integrating 4x squared with respect to x, and you're integrating 3 with respect to x. And you're putting all these together at the end to get your integral of the whole function. So that's just a kind of description of what you probably already do without thinking too much about it. So we're going to apply the same logic to this function here. Now you can see we're already getting straight in with cosine. We've got 3 over x. We've got this square root that we're going to want to deal with. So first of all, I'm going to say I'm going to integrate the 2 cos x. That's one of the jobs I need to do. Another job I need to do is I need to integrate the 3 over x. And another job I need to do is to integrate the square root of x, which as we know is x to the power of a half. Now we'll worry about this subtraction sign here when we get to the final answer. So we'll integrate these separately and then we'll just combine our answers together. Now you don't have to write this when you're doing this question, okay? All I'm doing this is to illustrate how to integrate 2 cos x, how to integrate 3 over x, how to integrate x to the power of a half. This one you already know how to do. So when we integrate cos x, we're asking ourselves the question, what would have differentiated to give us cos x? Okay, because integration is ultimately reverse differentiation. So if you ask yourself that question, then integration will probably never be too much of a problem. What would we have differentiated to get cos x? We would have differentiated sin x. How would we have differentiated sin x to actually get 2 cos x? Well, it would have been 2 sin x. And so if we just integrate 2 cos x, then we just get 2 sin x. Now, the great thing about integration is we can check our answers, because when you're confident with differentiation, you can differentiate this and just check that you get what you expected. So we differentiate 2 sin x, we get 2 cos x. Now, there is a little bit more going on here, which I'll get into in the next slide. But for now, we want to be able to integrate these ones just on site. All right, so we'll get to 3 over x. Now, what do we know that differentiates to something over x? That's the question. We know a function that when we differentiate it, we get 1 over x. That's what this kind of looks like. Yeah. Ultimately, you could write 3 over x as 3 times 1 over x, right? So the function that we know that differentiates to 1 over x is natural log. And so we have natural log of x. Okay, so if we know we differentiate natural log of x, we get 1 over x. To get 3 lots of that, we've got 3 natural log of x. Now there's something special about natural log that we have to be mindful of when we integrate. If we ever get natural log as a result when we integrate, we need to use modulus around the x, or around the function of x, whatever is there. The reason for that is because we cannot take the natural log of a negative number. So if we were to substitute a value of x in here, we'd have to make sure it was positive. Now you can substitute negatives in, so you could substitute x as -2 in here, but you would ultimately ignore the negative and you would use natural log of 2. Now that doesn't come up very often, but it can, and we'll get into that as we go through integration in the second year. But for now, remember when you integrate and you get natural log, put a modulus around your x's. And then the last one, we know that if we integrate x to the half, we add 1 to the power and divide by the new power, and there we go. So that means that our integral of 2 cos x plus 3 over x minus root x dx is all of these added together. So we get 2 sin x plus 3 log x minus the 2/3 x to the 3 over 2 plus c. Now, if you're wondering why I put plus c here, plus c here, and plus c here, well, that's just because I wanted to keep my notation correct. But ultimately, there's only 1 plus c at the end of the function. Okay, so hopefully that wasn't too tricky. All right, question B. We have this lovely cos x over sine squared x minus 2e to the x. So let's just separate this. For the sake of explaining how this works, I'm going to integrate these two separately, which is what you do in your head, like I said before. And then I'm going to put them together at the end. So we're going to integrate this, and we're going to integrate our 2e to the x. And then we're going to combine the results at the end. Cos x over sine squared x looks a little bit complicated. Now, the key thing when we're integrating trigonometry, and again, we come back to this in a lot more detail in the second year, but for now, when we integrate trigonometry, if it's sine and cosine, we just think, well, we know what differentiates to give sine and cosine. Okay, so we try and apply that, and that's what we've got here, but it's all tied up in a fraction, and we've got squared, so we need to be a bit careful. And the way that we're careful is we look at our standard results. So we're looking up something to do with cos and sine squared. Can't see anything to do with cos and sine squared. I've got a cosec squared, I've got a sec squared. So I'm going to have to try and rewrite this trig as something else. Okay, we're going to have to think about our identities. We're going to have to think cleverly about splitting up fractions to see what we come out with. Now I can see that cos x over sine squared x can be written as cos x over sine x multiplied by 1 over sine x. All right, split this squared up into two denominators. All right, so this, if we simplified this, we get this. Now you might be thinking, but why? How would I know how to do that? Well, and again, this kind of comes with practice, but I know that if I integrate cos over sine, remember, is cot, and 1 over sine is cosec. And if we have cot times cosec, I can integrate this to get cosec. So I knew what I was looking for, but only because I've done hundreds of these and because I've practiced. And you will get to see those links as you practice. So that means this becomes the integral of cot x multiplied by cosec x. Remember, cos over sine is 1 over tan, isn't it? So that's cot. 1 over sine is cosec. And that means that cosec x multiplied by cot x just integrates to cosec x. And again, we don't need any other proof for that. We're just using this standard result. Integrate 2e to the x. Well, we know that when you integrate 2e to the x, you're going to get 2e to the x. All right, e to the x differentiates to give you e to the x. 2e to the x differentiates to give you 2e to the x. There's nothing complicated going on there. We don't have any multiple of x in the power. We'll deal with that in the next slide or the one after. So let's combine our answers together. We had the integral of cos x over sine x, and I think it was minus 2e to the x dx. Let's just double check. Yes, indeed. And that then just becomes cosec x minus 2e to the x. Let's see. Just using those standard results and what we know about e to the x. Now, it'll take a little time at first. It will take practice. The next couple of slides, I'm going to show you what we do when we have results that aren't clearly obvious to the naked eye. Okay, just checking the timing there. This is going to be a long one. And you know that when I say it's going to be a long one, you're in for a rough ride. Right. Now we're going to look at what happens when we have things like cos, e to the power of, and a trig function that we have in our list. What happens when we have these and they're like 2x plus 3, 4x plus 1, 3x? How do we deal with that? Well, we have this lovely little technique where we guess. That might seem a bit silly, but yes, we make an educated guess and then we adjust our guess. So let's have a look at this first one. Cos of 2x plus 3 with respect to x. I'm going to make a guess here, and I want you to guess as well. Thinking about the fact that what do we differentiate in order to get cos? We differentiate sine. The easiest guess I can make at this is that the answer to this will be sine of 2x plus 3. All right, that's just a guess. And the only reason I'm guessing that is because sine differentiates to cos. And I know that the 2x plus 3 will go with it. What we have to do with this is we differentiate the guess to see what we get. So if I differentiate sine 2x plus 3, I get cos 2x plus 3. But using the chain rule, I'd have to differentiate the 2x plus 3, which gives me 2, and multiply the two things together. So I actually end up with 2 cos 2x plus 3. So, you know, I think it was a pretty decent guess, but actually we didn't get what we wanted. We should have got cos 2x plus 3, and we got 2 cos 2x plus 3. So what we do thirdly is we adjust the guess. So we go back to our original guess and we say, well, that when we differentiated it, that gave us a result that was 2 times too big. So that means we go back to our original guess and we divide it by 2. And this time what would happen is sine becomes cos, 2x plus 3 differentiates to 2, multiply the two things together, that 2 times a half gives us the 1, which is what we're after. So then we can just write the answer. That means our cos 2x plus 3 integral with respect to x actually comes out as 1/2 sine 2x plus 3 plus c. So we've got three things going on here. G stands for guess. D stands for differentiate. And A stands for adjust. And if you follow that little method, guess, differentiate, adjust, then you're going to get through the rest of this lesson absolutely fine. Now, some of you might have noticed, did we just see that that's 2x and therefore we divide by 2? I mean, let's find out. So for question B, we're integrating e to the 4x plus 1 with respect to x. So for this one, my guess, that instinctive guess that I've got is that e to the power of something differentiates to e to the power of something. So my guess, straightforward, is e to the 4x plus 1, right? Because that will differentiate to that. Let's check by differentiating. So if we differentiate e to the 4x plus 1, we get e to the 4x plus 1 as expected. But using the chain rule, we have to differentiate 4x plus 1, which gives us 4, and multiply the results together. So we get 4e to the 4x plus 1. So how far are we away from what we wanted? Well, we wanted 1e to the 4x plus 1, and we've got 4e to the 4x plus 1. So our adjustment here, go back to the original guess, and divide it by 4. So our final result, if we integrate e to the 4x plus 1 with respect to x, we get 1/4 e to the 4x plus 1 plus c. So that guess that we had on the last one kind of came true, didn't it? If we've got 2x, we divide by 2. If we had 4x, we divide by 4. And in most cases, it is that straightforward. But you always have to guess, then differentiate, and then adjust. Don't just steam straight in there and assume. Okay? So the third one we've got here is sec squared 3x. With respect to x. Now, what I should have put in here, I apologize for not doing that, but I'll do it right now, is we know this result here, which you may or may not be able to see. But there we go, editing on the so we have this result given to us. Okay, when we integrate sec squared, we know that it integrates to tan. So that's going to be part of our guess. Okay, that's how this works, right? We can use the formula book when we're unsure about some of our trig ones. So we make a guess for this. Well, my guess is, well, knowing that sec squared integrates to tan, my guess is simply tan 3x. Differentiate tan 3x, well, we can see here tan kx becomes k sec squared kx. So differentiating gives me 3 sec squared 3x, which you may have already predicted, given the 3, and that's using the chain rule. And the adjustment, therefore, is we must divide by 3. So ultimately, our integral of sec squared 3x becomes 1/3 tan 3x plus c. And again, it came true. We divided by the 3. So hopefully you're thinking, yeah, I can do this. I can have a go at this. And you'd be right. All right. Everybody has it within them to have a guess, differentiate their guess, and adjust their answer where necessary. You'll get the guesses more and more right as you work and as you practice. So now we've just got, I've got a couple more slides to go through because we're just going to have a look at what we haven't looked at yet. We haven't looked much at logarithms, and we haven't looked much at brackets to the power. So that's what both of these examples are. This question A can throw a lot of people, all right, simply because the dx is on the numerator. This actually came up in an edXL exam a couple of years ago, and a lot of people were thrown by it because the dx isn't in the usual place. But dx over 3x plus 2 is just 1 over 3x plus 2 dx. That's what it's asking us to do. It's effectively, think of it as multiplying the dx here. That would go on the numerator. So that's what we're doing. So now that we've got it in that fashion, we make our guess. Now, we know that when we differentiate natural logs, we get 1 over. Okay? Differentiating natural log gives me 1 over something, 1 over x, 1 over whatever it is. So my guess here is going to be natural log of 3x plus 2. And I'm just remembering my modulus symbol there as well. So that's my guess. That's as close as I can get for now. So differentiating that, okay, differentiate natural log, as we said, we get 1 over the 3x plus 2. But using the chain rule, we have to differentiate the 3x plus 2, which gives us 3, and we multiply the 2 together. So we end up with 3 over 3x plus 2. Now, how far away is that from what we wanted? Well, we wanted 1 over 3x plus 2, and we got 3. So as we got 3 over 3x plus 2, our adjustment becomes, as we did before, we're going to divide by that 3. So that means our integral of dx over 3x plus 2 is simply 1 over 3 natural log 3x plus 2 plus c. And again, if you made that prediction at the beginning, it's 3x, so we're going to divide by 3, then you were correct. So in this final one, we're going to have a look at this. 2x plus 3 to the power 4. So, you know, just looking at this, if I was to make a guess on this, I'm just going to up the power by 1, right? When we integrate, the most basic thing we can do, you know, this doesn't fit with any other pattern. There's no trig in it. There's no exponentials in it. There's no 1 over in it, so we can't use natural log. This is just a bracket to the power. So my instinct is telling me, what if I just raise the power by 1? That's what we do with integration after all. So my guess is just going to be 2x plus 3 to the power of 5, right? Up the power from 4 to 5. Now, of course, it's not going to be as simple as that, but it's a starting point. And let's see what happens when we differentiate. So when we differentiate this, we'll have 5 lots of 2x plus 3 to the power 4. But then again, using the chain rule, we have to differentiate the 2x plus 3 to give us 2 and multiply the 2 together. So we end up with 10 lots of 2x plus the 3 to the power of 4. So now we make our adjustment. We wanted 1 times 2x plus 3 to the power of 4, and we had 10 lots of 2x plus 3 to the power of 4. So actually, we're going to have to go back and adjust by a factor of 10. And so that means our answer for the integral of 2x plus 3 to the 4 is 1 over 10 times 2x plus 3 to the power of 5 plus c. Now that's where, if you were predicting that you'll divide by 2, we didn't divide by 2. And this is the exception to that rule. When you have this function in a bracket raised to a power, you need to take into account the whole dividing by the new power, because what I didn't do in my guess, and what I could have done but what I didn't do, was use the principle that you add 1 to the power and you divide by the new power. So my initial guess could have been 1 over 5, 2x plus 3 to the 5. And then I would have divided by 2 again to give me 1 over 10. But I thought, keep the guess simple, just raise the power by 1, differentiate, because I know this is always going to give me a numerical factor that I'm too big, so I need to then divide. And I think it's just the simplest way to do it. Okay, so for the rest of this lesson, it's practicing a mixture of those skills. That's all we're going to do. I've given you an example of each one, and now it's just about getting stuck in and practicing those. There is one more question that you'll see in the examples PDF that I will do. I have done as writing, so you can see what I've done for that example, and we will work through it in class if you're going to be in the lesson. But if not, try and use my working to work backwards from. All right, well done. I will see you when I see you. Here are the questions, by the way. Thanks a lot. Goodbye.